So that's all that I wanted to cover in the multi-objective optimization. The specific algorithm is too simple, so we will discuss the non-dominated sorting genetic algorithm called as the non-dominated sorting genetic algorithm. So it's just a genetic algorithm, so nothing to teach. You take a population pool, you do fitness selection, you do scaling, you do crossover, you do mutation, you do all those things. It's just a genetic algorithm. If I need to apply a genetic algorithm over a multi-objective optimization, the problem comes is that we had in our random algorithm, which objective do I use? They are M objective functions. Which one do I use? So it's just a genetic algorithm. The problem is which objective function do I use? With objective function as now there were two criterion, so I'll have the same two criterion in my objective functions. So the first is I had to get non-dominated solutions, so that's called as a Pareto rank. That's also called as a primary objective. And the second one is I had to increase diversity. There are two spaces, so let me say diversity in objective space. So the only difference is in the fitness function. So let's discuss the first fitness function. Again, there is a decision space I'm not drawing. It gets mapped to objective space. I am drawing f1x, f2x. And let's consider some individuals. So now what I do is I find out what is a Pareto front. So this is the one that has nothing in its bottom left. So this is non-dominated. This doesn't have anything in its bottom left. So this is non-dominated. This doesn't have anything in its bottom left. So this is non-dominated. This does not have anything in its bottom left. So this is non-dominated. This has this in its bottom left. 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 This has too many in the bottom left. This has too many in the bottom left. This has too many in the bottom left, which means these are the non-dominated individuals. And this is what my Pareto front is. And the Pareto front is called as a rank 1 Pareto front. So let me write down the rank 1 Pareto front over here. So that's rank 1 Pareto front. Now I delete this one and I say that in the new population pool after this thing, so just don't look at this thing, just don't look at these individuals. Let's calculate the Pareto front again. This has nothing in its bottom left. I know it is, but we have just neglected it up. This doesn't have anything in its bottom left. This doesn't have anything in its bottom left. This doesn't have anything in its bottom left. This has this in its bottom left, so no. This has this in its bottom left. This has this in its bottom left, so this is the rank 2. And similarly, this one is interesting. Yeah, it is in the bottom left, so that's a rank 3 Pareto front. So I delete this one and calculate the next Pareto front. So let's write the ranks down. And that's a rank 4. So this rank is the fitness function that needs to be minimized. This rank is the fitness function that needs to be minimized. So the entire problem in genetic algorithm was just to find out what is the fitness function. I have given you a fitness function, so that's done. However, there are multiple individuals which have a tie break. In fact, towards the end, all the individuals will become rank 1. because all the individuals will become rank 1, there will be a tie-breaking condition involved. All the individuals are exactly the same fitness value. So I need a tiebreaker. So that's where the secondary objective comes into play. And I will not deal with it because I've already said that the diversity is inversely proportional to the distance xi xj. And then we were submitting it over. So previously fitness sharing, we used one, use exactly the same one if you like. That's also called as the crowding distance. So further apart individuals don't contribute, the near individuals contribute. If the diversity value is extremely low, so it's 0 plus 0 plus 0, so it's extremely low, it's 1 upon 0, 1 upon 0, 1 upon 0, so it's actually extremely high. And because it's extremely good, we use exactly the same thing as previously. So just use the same as used in the fitness function value, where all that we say is that the diversity is inversely proportional to the distance. Now, the problem of complexity will come out to be in this case as well. So previously we said that we'll reduce it to the proximity where up to D max we'll take and after that we'll not take. And that's one of the things that you can use. What NSGA does it specifically is, in all the axes, it finds out which one is the closest individual for this distance calculation. So if I go in X in the positive side, this is the closest individual. If I go in X in the negative side, this is the individual. If I go in Y and the small positive direction, this is the closest individual. If I go it in the negative side, this is the individual. So these distance values will be the one used to calculate diversity, which means the complexity will not be n square. That comes when the individuals are very close to each other. You need to calculate distance between every pair of individuals. So the complexity is not n square. To calculate distance, between every pair of individual, for m dimensions it is mn square. To calculate these things, we did that in fitness sharing, so I'm not giving you the exact expression. It becomes, if you use this one, it becomes m into n log n, which is basically you sort all individuals across all axes and you look at the neighbors. So sorting is n log n, looking at the neighbors is n, so it's n log n plus n, which is n. And you need to do it for all axes. So it sort all individuals across all axes. So the all individuals is n log n, and across all axes is across m axes, m objective functions. So that's number of objective functions and number of individuals. So that's just a small complexity issue. That's just a small complexity issue. Now it turns out the major problem with the NSGA is not here. The major problem with the NSGA is that it is inherently an extremely slow algorithm. So it's a normal GA, so it does selection based on fitness calculation for a number of times. So that's while stopping criterion. So while stopping criterion, there's a fitness calculation, there's a selection, there are genetic operators, crossover mutation. And selection of new population pool, sometimes based on children and parents combined. Now, it turns out in NSGA there is actually no fitness calculation because I did not give you a fitness function, but selection is still possible because I sort all individuals based on, so I sort all individuals based on Pareto rank, and so that's primary. Diversity, so that's a tiebreaker, which gives me ranks, and you know expectation is proportional to rank. So my first step is sort all individual based on Pareto rank as a primary criterion and diversity as a tiebreaker. This gives me rank. So this gives me rank, and I know that expectation is inversely proportional to rank. So which one is a computationally expensive step? So first I need to sort all individual based on a primary criterion and a secondary criterion. That will give me a rank, that will give me expectation, inversely proportional to rank. We've seen that before in genetic algorithm. Then of course, once I've got the expectation value, I do a selection, genetic operators, and the new population pool, where for n individual, this is O of n, this is also O of n, the way that I was doing it up. So I need to calculate the complexity of this step. So I need to calculate the complexity of this step. Previously, selection was n log n, and that was where my, so the two selection problems were previously n log n, that was the bottleneck, and that's where the complexity was coming out. Now let me say, for this algorithm, for this sorting, what is the fitness function value? What's the complexity? A normal complexity of by any sorting algorithm is n log n. So that's my normal complexity. Now I'll need to see does anything need to be changed for this particular step? Now this also step has two parts. First I need to calculate the Pareto rank of all individuals. So I cannot do sorting unless I have the Pareto rank, and then the diversity as a tiebreaker. Diversity as a tiebreaker, we have already seen that by sorting individuals, the distance between every pair of individuals can be calculated in O(n) time, because every individual will only look at its neighbors. So it doesn't really bother me up. It doesn't really bother me up. I have already made this a O of n operation. To calculate the diversity of every individual, I have already made it as a O n log n operation. Sorting itself is O n log n, and the diversity calculation of all individuals is happening before sorting. So calculating the diversity of all individuals, I have made it as an n log n operation by sorting all the individuals on the axis, and that's exactly the same as sorting all the individuals later on based on this as a comparator function. So Let me calculate the only complexity which is not calculated, which is around over here. So let's write this step a little bit more clearly. So I say calculate Pareto rank, otherwise I cannot sort, of all individuals. Calculate diversity. Of all individuals. That became n log n by sort by axis. And check neighbors. And then sort population using values calculated by 1 and 2. So let me give you the complexity of this one. So calculation of the Pareto rank. So the complexity of the calculation of the Pareto rank is a difficult complexity. So let's say that in what time do I find out if an individual dominates another individual? So I'll travel on all the axes and I'll see that this one is either significantly better than this in all the axes, or this one, basically this one is better than this in all axes or equal, and there's at least one axis where this one is significantly better. So this is OM operation, which is dominance. So to find out if xi is non-dominated, I'll have to check all individuals and find out if anybody dominates xi. So I'll have to iterate on all individual to find out, is there any one individual which dominates xi? If yes, then it's gone. So it's O of nm, where n is for iterating all the individuals, and every individual I use this to calculate dominance, so it becomes O of nm. So thereafter what do I do is I find out all the individuals which are non-dominated. They are rank 1, so I get all the individuals which together turn out to be rank 1. So rank 1 individual calculation. This is to find out for one xi. I need to calculate this for all xi's possible. So n square m. Nm is to calculate whether xi dominates, whether one individual dominates. I need to check for n individuals which of the n individuals dominate. So it's O of n square m. Similarly, rank 2 individuals will be n square m. Rank 3 individuals will be n square m. And how many total ranks are possible? Maximum number of ranks possible are rank n. So it's O of n square m plus O of n square m plus O of n square m. So this is n cube m complexity, and that's too large. So far, sorting population using this n log n. This was n square, but I could reduce it to n log n. This one is n cube m, that's too large. Now, there's a variant which is called as the second edition of the NSGA, or the NSGA2. It uses an algorithmic trick, and because it's purely algorithmic, that's why it's not of my interest over here. So the algorithmic trick to reduced complexity. I define a new data structure that stores number of individuals So I store in a new individuals and that stores the number of individuals that dominate an individual xi. So if this metric is equal to 0, no individual dominates xi, that means it's Pareto rank 1. And list of individuals that xi dominates. Whenever I delete an individual from the population pool because it's in Pareto rank 1 temporarily, whenever I delete an individual because it's Pareto rank 1 to calculate the next Pareto rank, I know all the individual that xi was dominating and I reduce this by 1 for all those individuals. So deletion becomes O of n operations. And finding out rank 1 is itself O of n operation because it's all the individuals such that the first value is equal to 0. So it's not going into any detail at all. It is absolutely and absolutely a algorithmic trick. So if you use this algorithmic trick, the complexity gets reduced. I'm not going into any detail. So multi-objective optimization, all that I need to do is I need to get a Pareto front of individuals which are nicely spread apart from each other. All that I need to do is I need to get in a Pareto set of individuals which are nicely set apart from each other like these blue ones, and I do it by using a simple genetic algorithm, no change to that. The only thing is, the only control that I have in a genetic algorithm is which individuals are good, which individuals are bad. So individuals which are diverse in the objective space are good, but then that's a secondary measure. The first measure is that the individuals which are in the Pareto front are the best because they can be returned directly as a solution. So individuals in the Pareto front are the best, they can be reduced, they're given directly as an individual. Then I had to define a metric such that the further away an individual is from the Pareto front, the poorer it is, and that got solved by Pareto rank. So it's a normal genetic algorithm that uses Pareto rank as a fitness function, where the more further apart an individual goes, the lower its rank, and the poorer it is, and the higher it is at the Pareto front, the better it is. So the NSGA algorithm is nothing but a genetic algorithm that uses the Pareto rank, or individuals closer to the Pareto front are given a higher fitness value, a better fitness value. Individuals further apart are given poorer fitness value. However, there's a notion of diversity already, and because there's a notion of diversity already, therefore I take diversity as my secondary objective, which comes into being when there is a tie in my primary objective. So using a mixture of Pareto rank, how close an individual is to the Pareto front, and diversity, how further apart from the individuals in the objective space an individual is, I run a normal genetic algorithm, and that is the NSGA algorithm, which gives me a nice Pareto front of these individuals. I can use metrics like generational distance, inverted generational distance, to find out how good or how bad it is. Sometimes, of course, we use a tertiary measure, which is fitness diversity in the decision space. So it becomes Pareto rank, diversity in the objective space, and diversity in the decision space. And the previous lecture on diversity was entirely onto why diversity in the decision space, and that's already presented. So a mixture of these three objectives: Pareto rank, diversity in the decision space, diversity in the fitness, diversity in the objective space, and diversity in the fitness function. So using three things, which is Pareto rank, so how close an individual is to the Pareto front, then you've got diversity in objective space. So that's my criterion for deciding a solution is good or bad, so I need to insert it up. And something that I did not speak about because it was already the previous R, which is diversity in the decision space. So using these three things, you get into a normal genetic algorithm that does everything that you expect a multi-objective optimization to do. So that's fx, and this is just x. So that's x1, x2, x3, x4, and this is f1x, f2x, f3x, f4x. So a normal genetic algorithm which optimizes between these three objectives, it makes sure the individuals first come close enough to the Pareto rank because that's my objective function. So if you simulate this algorithm, this is what you'll see. Earlier, everything is random. I'll not show it in the objective decision space, I'll only show it in the objective space. So this is f1x and this is f2x. So these individuals get rank 1, they are superior, and these are very bad. This is rank 3, so they die. And instead they form new offsprings which are intermediate. So then also these individuals are very far off, they are rank 3. So they form in offsprings. So first all the individuals try to come because of the primary objective closer to the objective space, which transforms the objective space into something where individuals are either rank 1 or rank 2, so there's nothing differentiating between them. Oops. So this comes into a position where all the individuals in the simulation are rank 1 or rank 2, and therefore there is nothing differentiating between them. Now what they do is, since the primary objective is almost the same, now we come on to the secondary objective where there's a pressure. So these individuals are good because they are sparse, and these individuals are bad because they are dense. So the individuals start spreading around with each other. So that's the first force that happens. So that's the first evolutionary pressure to reduce rank. And that's the second evolutionary pressure. Based on the secondary criterion to increase diversity. So first there's an evolutionary pressure. Why? Because of the fitness function that I've taken, where the individuals start coming inward towards the Pareto front. They may be moving anywhere in the decision space, I cannot tell you about it. So first they come closer towards the Pareto front, and then they diversify in order to maintain it up, and this is exactly what my ideal solution is. So if any individual moves a little bit here and there, its diversity is going to reduce. If it moves backward, its Pareto rank is going to reduce, so the individuals feel a pressure to be exactly at the place where they are currently located at. And that is, of course, the non-dominated sorting genetic algorithm.